In this paper, we focus on the problem that a robot may fail while executing everyday actions, for example while opening drawers, even though it might be following an optimized execution policy. The motivation is that an intelligent autonomous robot should be able to analyze its execution failures and, whenever possible, improve the execution policy based on the analysis. We use a representation of parameterized execution models, which we introduced in our recent work, and present methods that make it possible to diagnose execution failures and use the results of the diagnosis for proposing corrections to the execution parameters which led to the failure. Given the parameters which led to an execution failure, the proposed diagnosis method searches for alternative action parameterizations until it finds a violation of the action's relational success model. Once a diagnosis is found, a correction of the original execution parameters is suggested by searching for parameters away from the direction in which the violation of the model was identified. The corrected experiences can be seen as synthetic data that can be used for learning a richer success prediction model. We illustrate our approach in the context of grasping a drawer handle. In this case, the robot ends up a bit too far and too much to the left. To diagnose the failure, we initialize a local search process for parameters, in this example alternative grasping positions, which violate the known relational success model. For this, we sample alternative parameters within a given search region and check if they violate the relational model. If no violations within the search region are found, the region is expanded and the search is continued. In the correction process, we first take the direction in which the parameters were moved for the violation of the relations to be found. We then sample alternative parameters away from this direction and weigh them based on the current success prediction model. The alternative parameters with the highest predicted success are then taken to represent a new synthetic execution sample with a high expected execution success. Using the proposed approach, we aim to allow robots to use their own failures as a learning opportunity. In particular, corrected experiences can supplement an already existing set of successful executions and may be used for lifelong learning of parameterized execution policies. Additionally, explicit failure diagnoses contribute towards a more transparent robot execution process, which can be beneficial for robots operating in everyday environments.